Be here at ICTS. It's my first visit here. So I'm really happy to be here. I was not here for the school. I'm going to tell you about some of the experiments that we have been doing in the last 8 to 9 months, looking at what seems like a quantum Hall ferromagnetism in very clean trilayer graphene. So I gratefully acknowledge the support from the Department of Atomic Energy and Department of Science and Technology that makes this work possible. So as I always say, I don't really do much work at all, and so the people who do the work are sort of deserve credit. And Biswajit, who's here, has done all the experiments, and this is the rest of my group. I justify my existence in the group by being the photographer on group hikes when we go out. So it's a pretty useful justification. We have greatly benefited from collaborating with Rajdeep and his students Santanu and Abhishek, who have provided kind of detailed calculations to support or rather understand the work. And we get some really magical materials from this group in Japan, who supplies the boron nitride to pretty much everybody in the world. So we gratefully acknowledge there. Okay, so let me quickly give you a brief outline to the work. Since there are a lot of students here, I'm going to have a little bit of slides of pedagogy there, but it's mostly a research talk. I'm going to talk about sort of a big picture of why one should care about, if people have tolerated graphene, why should anybody tolerate multilayer graphene? What is exciting? I'll try to give you a brief context. Then I'll try to kind of make a case which is pretty obvious to this audience is why we need clean devices. It can provide, kind of a window into new physics which not been seen before. Then I'll talk about our experiments, what we understand, and how we understand it. Oh, and I'll also have a slide at the end pointing out aspects we don't understand. Okay, so if you have any insights, please, or thoughts, please do let me know. Okay, so let me get started by just showing the slide about graphene. So everybody knows about graphene, the unique band structure that it has, and people have probed the physics of the electronic transport in graphene extensively. So one of the nice things about as an experimentalist is the ability to make devices where you can continuously tune aspects like the energy, Fermi energy, continuously. And that's possible because most of our measurements will have geometries, and I'll show you devices later, which are basically a slightly more complicated version of this device geometry, where you have source drain electrodes through which we measure transport, and then we have a gate electrode which essentially continuously dopes the material over a range of charge densities. So this is our knob to the Fermi, kind of tuning the Fermi energy continuously. Okay. So what one experimentally measures for the case of graphene, of course, is that as one tunes the Fermi energy, one can have a region of conduction due to holes when the Fermi energy sits in the valence band, and you have conduction due to electrons when the Fermi energy sits in the conduction band. Okay, so this ability to tune different regimes of transport involving different bands is one of the nice things. This is not entirely new to graphene. People have been doing it, but it really comes out to great effect in these experiments. Okay, so and the experiments that I will show you will have this knob extensively used. So sort of a brief introduction to trilayer graphene, and this will also make a case for why, what's the interesting thing about many layers of graphene stacked on top of each other. So in case of many layers of graphene, you have an option of stacking. This is another degree of freedom that you have, whether you have an ABA kind of stacking or an ABC kind of stacking. So just the stacking kind of fundamentally changes the electronic transport properties that you will see and the band structure. And for example, for ABA stacked graphene, the bands look like this, and this is our sort of hero for today's rest of the talk. We will be talking about measurements on ABA stacked graphene. And this is the band structure of, or in general, ABC stacked n-layer versions of graphene. So first of all, there is kind of this sort of electron-hole symmetry that was there in monolayer graphene and is there in ABC stack is no longer there for this. So it kind of breaks some symmetries, which is kind of interesting and fun. But primarily to motivate why these are interesting is that in general, the dispersion relation can be tuned if you have many layers of graphene. And you can kind of use that to tune the relative importance of electronic interactions, which can lead to exciting physics. Okay. And so that's sort of the big picture idea that we want to use, is to use multilayer graphene as a playground to look at effects of electronic interaction, and which will sort of key to the physics that I will talk about. Okay. So the big picture in this talk is that we will have a situation where we have Landau levels arising out of two different origins. Oh, sorry, I forgot to emphasize, but I will do it later. There are bands which are monolayer-like, which are these conical, and there are bilayer-like bands. So in our experiments, there will be Landau levels which arise from monolayer and bilayer, and they will actually become near degenerate. So when they're far away from, so imagine these are the two bands, when they're far away from degeneracy, the exchange energy doesn't play an important role, but when they're close by, exchange energy becomes an important parameter, and you can actually get sort of ferromagnetic states within the system. And again, as you tune another parameter, you can basically tune out the relative importance of exchange interaction. And that's really, so similar physics has been explored in semiconductor 2DEGs. So what's exciting for the case of graphene is that energy scales in graphene are different, and so they allow you access to a parameter regime that was inaccessible earlier. So I'm not going to spend too much time. If you're interested in experiments, details, please do ask me, and we'll be happy to tell you and share with you what we know. So to make very clean graphene, we use a technique which was developed in Colombia, and it basically involves sandwiching graphene in between boron nitride. Okay? And that basically encapsulates it, and part of the thing is that the graphene that is encapsulated doesn't really see any impurities, and there's very little scattering. So that gives you very high quality graphene. And it's literally sort of a handicraft project which takes a long time, and Biswajit is a master at it, is to essentially pick up one layer at a time and kind of put it together. So it's painstaking and takes time and patience. So you pick up take up kind of a rubber stamp, pick up one layer, pick another layer, and that basically gives you the sandwich structure. Okay, that ensures that the cleanliness of the system is very good, and I'll show you what we mean. So this is the end result of it. Although we follow the work done by Columbia Group, we have kind of our own sort of innovations or tricks that allow us to make devices in slightly different ways, which I think results in very clean devices. So these devices in multi-layer graphene, achieving high mobility is tricky, but we believe that we can get really high mobilities. And I'll show you when we start talking about the quantum Hall physics, how this is reflected in those measurements. So quantum Hall basics are very straightforward. Earlier, for the case of monolayer graphene, and it holds for any system, is that you have a continuous density of states. For the case of monolayer graphene, they look something like this. And as you apply a magnetic field, you get the cyclotron orbits, which quantize, and you get these Landau levels. And in case of monolayer graphene, they're not equally spaced. And that's basically because the zero magnetic field density of states is also has a very peculiar structure, unlike the conventional 2DEGs that we know, which have a constant density of states as a function of energy. So once you get the Landau levels, they have some width which is determined by the disorder in the system. So that's the intrinsic Landau level width. So in terms of the transport measurements, what we do is, and I won't talk too much about it, is we make electrical connections that I shown you earlier, and we measure the transport through it. And so you basically, as you tune the Fermi energy by the back gate, you will basically pop out or pop in Landau levels, and that's reflected in the transport through the system. And you will have one Landau level or two Landau levels, depending on how many Landau levels are actually filled up, depending on the magnetic field or the charge density that you have in the system. So, but for the rest of this talk, we will kind of not worry too much about the edge states. We will just use the electrical transport measurements to probe, which is the longitudinal resistance, Rxx, or sigma xy, which sigma xx, which denote the position of the Landau levels as a function of magnetic field and gate voltage. Okay, and the sigma xy or Rxy tells us about the degeneracy within the system and tells you what is the overall filling factor within the system, and that we use extensively to probe the system. Okay, so that's basically all that I'm going to talk about as far as quantum Hall physics. All we are going to invoke is that you have a kind of discrete energy level spectrum in the arising out of the quantum Hall effect, and we're not going to worry too much about the edge state transport itself, but it's a probe for seeing what's happening inside the system. So I want to set out the energy scale. So this is sort of the previous work which was done in monolayer graphene, where this is En is the Landau level spacing for the first gap in monolayer graphene. This is the interaction energy, sort of the Coulomb energy scale. This is sort of an energy scale which is set by corrugations that the electron gas is, or the whole gas is sitting in a landscape which has atoms. And then, of course, this is the Zeeman energy. And this is typically the disorder broadening that was measured in earlier experiments. So this is an important energy scale because the physics arises from the relative ratios of these energy scales, and the primary energy scale is the disorder. What we, in our devices, we see that our disorder energy scale is significantly lower, which allows us to explore physics at lower magnetic fields and in a slightly different way. Okay, so the crystal structure of A stacked graphene is something that I've already kind of shown you. So it's 3 layers of graphene stacked on top of each other. So the zero magnetic field band structure looks like this. Again, pointing out there are monolayer-like bands and bilayer-like bands. And as you apply a magnetic field, so I just want to orient you, this is the magnetic field, and this is the energy. And again, there is no electron-hole symmetry, so the system is, at zero magnetic field is not symmetric to begin with. This is what the Landau level spectrum, the black lines are the Landau levels which arise out of bilayer-like bands, and the red lines are the Landau levels that arise out of the monolayer-like bands. And so they, as a function of energy, they will intersect at different points. What I want you to pay attention to is that this zero energy monolayer, zero Landau level, n equals 0 for monolayer, is already split at to begin with. Okay. And it will intersect a wide variety of Landau levels which are from bilayer-like. And when they cross each other, there is going to be interesting physics that I will talk about, okay? So once you have this as sort of background, I want to kind of quickly show what people have done before, just to give you a bigger context of what people have seen before. So people saw in relatively modest mobility devices, they saw hints of these Landau level crossings, which were used to infer properties of the band structure. So once you know the energy scales for the Landau level crossing, you can actually calculate band structure parameters relevant to graphene. People have studied sort of some details about the band structure from these measurements, both for ABC and ABA stacked graphene. So these are our measurements. So these are measurements where which as a function of magnetic field and gate voltage on the electron side, and you can see Landau levels, lots of Landau levels starting from around half a Tesla, and you will see another set of sort of envelopes which are parabolic in nature. So these are the intersection points of the monolayer and bilayer-like bands. Okay, typically when you measure sort of these experiments, this axis is gate axis, which is charge essentially proportional to charge density and not really energy, and it takes some time to kind of go back to the other energy back and forth. So what's really happening is now we can go ahead and identify what are the different Landau levels or crossings due to different Landau levels or bilayer. if we take slices of this different, we can identify that this is indeed the case, what we expect, that these are intersection of monolayer by finding out what are the jumps in RXY at each of these crossings, because that tells us what is the net change in the filling factor of the system. Okay. So we can do that on the whole side as well, and it kind of makes sense. We can completely understand the system. We can put in sort of calculated spectra and compare it with experiments, and that way we can get a confirmation of the band parameters that we have to start talking about the next set of sort of experimental results. So now, as we crack, so this data is only up to 1.5 Tesla, which is basically a thin slice here. Now we can go ahead and crank the magnetic fields to very large values. Okay. So you see, this is sort of the fan diagram, the Landau levels of the system as a function of charge density and magnetic field. And these are, again, the different Landau levels. And what you would notice is at this point, a gate voltage of around 10 volts, you see sort of a glitch, and it continues and it kind of propagates up through the system. Okay. And that's sort of the interesting crossing points that I kind of alluded to, and we'll come back, revisit this, and look at it a little bit later. And we see lots of crossings of the different Landau levels. Okay. And this is sort of the crossing of the Landau levels, and I'll tell you in a little bit why that's interesting and why you should sort of care about it. So if you look in a little bit carefully at this region, you'll see finer details emerge. One sort of common sort of feature is that we see a fourfold sort of n equals 0 Landau level, which is all the degeneracies have been lifted all the way at something like 2 Tesla. So we also see regions which are closed loop surrounded by the crossing points of different Landau levels. And one can look at them a little bit carefully further and identify from independent measurements, which is of RXY. This is kind of RXX. We can label the filling factors by doing the RXY measurement. And so we know what the filling factors are, and we know exactly what's happening. But at these points, the red points are kind of resistive regions. There is dissipation within the system. Blue is kind of dissipation-less, near dissipation-less transport. Okay, so now we go ahead and try to understand what's going on. So this is sort of the band structure in the absence of a perpendicular electric field. So in ABA, stacked graphene, trilayer graphene, you can bake the overall symmetry by applying a perpendicular electric field. Okay, so in our experiments, we are very close to the electric field equals 0 regime. So this band structure is a reasonable approximation. So this is sort of what happens when you have lots of Landau level crossing. When they cross, become near degenerate, you will get a kind of avoided crossings, and there are lots of avoided crossings. And so the net result is the evolution of the n equals 0 Landau level, which is of the monolayer, follows this kind of contorted path, but it's the n equals 0, which has all the degeneracies are already lifted, and these are the various bilayer-like bands here. This is spin polarized bilayer-like band. I can tell you the details later, and it intersects with these monolayer-like bands. And all of these, many of these states here and enclosed regions are actually ferromagnetic ground states, as I will show you in a few minutes. Okay. So what's really happening in the system is that we can go ahead, based on the filling factors, we can go ahead and identify what it is happening. So so I showed you a complicated picture earlier, but this is a kind of a simplified, easy to kind of understand picture of what's happening. You have a bilayer Landau levels n equals 2, and it intersects these polarized monolayer Landau levels. And we can go ahead and write down the configuration, electronic configuration of the band, different Landau levels in these different states. And we find that all of these 3 states here are ferromagnetic states. And we can actually try to write down what are the net spin configurations within the system. So these states, which are sort of completely closed loop, they're fragile. in the sense that if we try to calculate or measure the activation gaps, these are much smaller than the activation gaps that we experimentally measure here. So we basically, to measure the activation gaps, we vary the temperature and find out what is the activation energy associated with each of those states. So these are fragile, they're ferromagnetic. These signatures of resistive states as a crossover point between these two different regions is kind of transport dominated along the domain walls that are formed within the system. So in these systems, you can, depending on the symmetry of this overall system, you can have either uniaxial anisotropy for the ferromagnetic state, or you can have an easy plane anisotropy. So we see, we haven't completely kind of watertight way identified what the anisotropy in each of the region is, but some of these boundaries involve crossover from uniaxial and an easy axis anisotropy. These are kind of interesting regimes because there is an associated quantum phase transition within the system. So, so we know that these are ferromagnetic. And then just to kind of support some of my earlier statements, our measurements of the sigma xy actually allow us to infer directly that all the symmetries have been lifted in these states here. And we can even go in and go here and identify these that the symmetries are broken way down in low magnetic fields around 2 Tesla. So now we can go ahead and try to do some measurements kind of to check for some hysteretic response in these systems. So we can do measurements here where these states. So I haven't really talked about, to be fair, what's happening on the whole side. That's some other part of the story that in this talk I won't focus on. But this is the electron side. And we see hysteresis associated with the electronic transport, where the states are ferromagnetic. When the state does not have any ferromagnetism associated with it, we don't see any hysteresis. And this kind of makes sense. Way back down here, again, where all the symmetries were lifted, these are also, some of them are ferromagnetic states, and we see hysteresis associated with that, but not any hysteresis with where all the symmetries have not been broken. So this is another kind of evidence for the ferromagnetic states that are associated. So just to get back as I close, so this is sort of where we are. We can infer some energy scales, and some of this work is actually, I didn't really talk about, but is done by Rajdeep, where they can actually do some really microscopic calculations and can infer magnitudes of exchange energies in different regions and their relative importance. We can infer, oops, there's a typo here, it should be bilayer. So something peculiar we notice, and it's at some level it's not too surprising, is that the Landau level broadening for monolayer and bilayer bands is quite different, and we can actually pick it out. So how scattering impacts monolayer and bilayer-like bands simultaneously can be actually seen in our experiments. So what we don't understand, and I want to spend a bit of time just talking about it. So to understand the importance of exchange, we would like to kind of measure the G factors, which are a little bit tricky to do from the experimental data, because as I said, this axis is not really energy, but something like integrated density of states or charge density. We would like to, in the future, try to also involve a perpendicular magnetic field and ask what is the nature of the quantum phase transition as we go from ferromagnets, quantum Hall ferromagnets, which are easy access, to easy plane. Okay? At these boundaries, you are also the places where skyrmions can be generated within the system, and those would be interesting to probe. And we don't have a good way to kind of play around with it right now or measure them directly, but we would like to do that in the near future. I didn't talk about it, but at high magnetic fields, we do see sort of hints of fractional quantum Hall effect at around 13 Tesla, where these spin polarized monolayer Landau levels start developing another set of substructure. So that's something that we are actually very keen to explore. So let me just summarize. This is sort of what I promised to tell you about, and thank you for your attention.
questions?
Yeah. Yeah.
So can you actually identify which are the occupied levels for
Yeah.
these different parts?
Yeah, so we can. So this is the nu equals 6 here, and we can identify, these are much easier to understand because we can write down, because it has some bilayer bands involved and no monolayer band involved, whereas this guy has all 4 degenerates. So we can identify. So this is the nu equals 6 occupied. Unoccupied levels are not kind of. Yeah, this is his. So we can indeed go ahead and identify these.
Okay. Other questions?
You said there's an easy plane to easy axis transition. That is as a function of the field or what? I mean, that is, it prefers an easy plane at low fields and then makes a transition to easy axis at...
Let me be upfront that we don't have complete watertight proof. We know what the occupation of the states are in different regions of the system, but we don't have a confirmatory proof that it's easy plane. But from symmetries, there are arguments, well-known arguments for classification of quantum Hall ferromagnets. So we are using that to say. So now, how do I go from easy plane to easy axis? Is if I just sweep the gate voltage. I go from, let's say, this region, which is completely spin polarized. And if I go to this, it's a slightly different set of symmetry. And as I go across this boundary, there are predictions for a quantum phase transition, just a gate voltage. No, I mean, you can traverse either with a gate voltage or a magnetic field. But here, I can just, by doping it.
Okay. Other questions?
Does that answer your question? Okay, the short answer is sorry? Yeah. So, yeah, so yeah, you have a good point. So there is a whole zoo of classification of the quantum Hall ferromagnets that Alan MacDonald classified in the integer quantum Hall, and they came up with a nice classification set of rules depending on the symmetry of the Landau levels that are crossing, are in the vicinity, whether it's likely to be a easy axis or an easy plane ferromagnet. So based on that, you can have quantum Hall ferromagnets which are either easy axis or easy plane. So it's nothing peculiar to graphene that is being used here to explain the easy axis or easy plane. I can give you the reference.
Okay. Any other questions? Anything? If not, let